the tab for orbitals we'll get to later on in this unit. But when I click on isotopes, now the weight, how much it weighs, goes now, like iron now has like the number 7. That just means that iron can have 7 different forms, 7 different versions of different numbers of neutrons in its nucleus. So there you go, iron. Okay, where they all have the same atomic number 26, but you see the 54, 55, that's the mass number. The 54 through 60, that is just changing the number of neutrons in an atom of that type of iron. So I think that's cool. But I am easily impressed. So, like with iron, you've got 7 different options for kind of versions of iron. They all have 26 protons in their nuclei, but they have different number of neutrons. So we need to be able to specify which isotopic form we're dealing with. So how do we do that? Well, all we got to do is say the mass number, because the mass number tells the kind of number of neutrons there are. So for instance, one solid isotopic form of carbon is one that has a mass number of 12. So we would call it carbon 12 like that. We could call it carbon 12 like this. We could call it carbon 12 like this. Now notice they're actually, in this version, we have the symbol for the element. And actually this version at the end here is the one we're going to kind of stick with. So we do the symbol of the element, and then we have the 12 is the mass number, and that's the number of protons plus neutrons. And then kind of redundant, we have the atomic number. And the atomic number is the number of protons. So that's kind of what we go with. This is showing you that last version where we had carbon 12 and 6. 12 was the mass number. Remember, that's the number of protons plus neutrons. Protons plus neutrons, and this is just protons. Okay. So again, you kind of have to, it's weird, you have to think of, anytime you see a Z, that's the atomic number. Anytime you see an A, that is actually the mass number. Don't know why they do that. So on a test or on your homework, you should be able to kind of find your way through this. Do you guys have the answers here already? Okay, so let's kind of go back and forth. Okay, we'll start with you, Quinn. What is the atomic number given this information? 9. It is 9. Very good. What is the mass number? RJ? 19. Perfect. So Quinn, back to you. How many protons does it have? 9. Very good. And I'll talk more about this, but the fact that there's no charge up here, if it wasn't neutral, there would be a charge up there, like a symbol and a number. So how many electrons does it have as neutral? 9. It also has 9. Okay, now this is the hard one. How many neutrons does it have? 9. Nope, not 9. 10? Why 10? No, why 10?
Because you say that's not like.
Yeah, sounds like you got it too, Quinn. Yeah, you take number of protons from the mass number. Yep, that's it.
We're just taking the atomic number from the mass number.
Right. Yeah, that's it. Okay, we'll have another one coming up next week. So boron, we can find it on the periodic table. So it's got 5 protons, so I'm trying to show you 2 different versions of boron here. This one has 5 protons and 5 neutrons, so this would be boron 10. And this actually has 5 protons and boron, and then it has 6 neutrons, so it literally would weigh more. And now its mass number is 11, so it's boron 11. And these will be due Monday.
So we have class one?
Yes.
Okay.
Are the schools out for that President's Day?
They normally would be, but because we've had some snow days,
Okay.
we're doing class.
Yeah. I told my class before y'all, it's almost like I can't. Teachers are all, we're gun shy, like we're gonna get force cancellations, everything. So I don't know. We just gotta keep going. No break for the weary, no rest for the weary. It's not a casual sort of lecture like sometimes some semesters is. So I call this the decimal number in the box. Decimal number, that's what I'm trying to say here. So your most periodic tables, I'll start to say, is that black and white one you're going to get for your test, will have the symbol. So like we pick on iron, it's going to say Fe, it's going to say 26 number of protons, and then it's going to say 55.85, and that is actually on average how much an iron atom weighs, and that's its average atomic weight. But I think we talked about, I introduced this, we can't weigh atoms in kilograms or grams because atoms are so light. So we introduce a new method of mass, or new mass measurement. And AMU stands for Atomic Mass Unit. I think I said this the other day, AMU. And the symbol, like the more current symbol, actually is the letter U. So sometimes you'll see, like if I pick on iron, I say it weighs 55.85. I could say AMUs, or I could say U's. So you'll kind of see that both out there. But I'm going to have to tell you there's a little bit of, it's not magic, but there's a little bit of consideration that goes into coming up with an average atomic weight, because we have to recognize that we have different versions we have the concept of isotopes out there. Okay. So average atomic weight, sometimes called average atomic mass, atomic weight, or atomic mass. Okay. So the fact that we have different atoms of iron out there, we decided there's like 7 different isotopic forms of iron. We have to consider how much of each form there are. Consider a weightage. It's called a weighted average. No pun intended. What about the weighted average? So an AMU, was it Wednesday? I think we introduced atomic mass unit, and that's a good way to measure how much one proton or one neutron weighs. One proton and one neutron weighs about 1 AMU, a little bit more than 1 AMU. By definition, that actually mass unit came from considering one form of carbon. And if you have one form of carbon isotope 12, then this is the middle of my carbon atom. It has to have 6 protons since it's carbon. And the fact that it's carbon 12 means I must have 6 neutrons. 6 in my nucleus. So that is my carbon 12 nucleus. It weighs exactly 12 AMUs, 1 atom. So electrons, I have 6 of these too, but their mass is negligible. Something like that. And then everything kind of builds from there, or is related back to that. So aside from the whole definition of an atomic mass unit is very small, if I were to say we'll have only one little atomic mass unit in terms of something that we can sink our teeth into in terms of a gram, I have just a fraction of a gram. Well, 1.661 times 10 to the minus 24th of a gram. But this other one's easier to remember, and actually on Monday, when we start to talk about a mole, this number is going to come up again. But if I have 1 gram, which is something you can sink your teeth into, in terms of units of atomic mass units, I have 6.022 times 10 to the 23rd atomic mass units. All right, so I need to kind of talk you through how do we come up with that decimal number? How do we do a weighted average, for instance, to come up with, for iron, it on average weighs 58.85 atomic mass units. Well, it goes down to those cards I gave you. Kind of look at the, pick on iron. So do you see 7 there for iron? only see 3. Let me see. This has 3 isotopic forms. Where is it? This is not. Okay, so if you add those percentage abundances for iron, do they add up to 100% hopefully? Please, God. Oh, no, I can't really notice. Yes. Yep, so you add 5.9 plus 91.7 is 2.1.
99.7.
Ah, yeah. It's not 100. So maybe that's why they kind of put the 3 most abundant, but it's lacking a few percentage. So that's consistent with the fact that when we went to that P table, it said there should be 7 different isotopic forms. That only showed 3. But they showed by mass number. Yeah, so mass number 54, 56, 57. Okay, very good. Well, in order to come up with how much an iron atom is going to weigh, we have to kind of take into consideration those are what we call the percent abundances. Okay? So for anytime you're given a percent abundance, whether it's for any element, it's going to break it down into different isotopes. And what they did was they gathered a representative, like from nature. There's a whole, there's an art or science to sampling. They sampled iron atoms, and they put all the iron atoms down here, and then they broke them out into their different isotopes. And so up here, they put the different isotopes, so they come up with those percentages. Okay, so that's when they got those. And if we pick on copper, so if you pick on copper, does your copper look like this? I've got 63, 65. Copper. What the fuck? This one is too. 30.8, yeah, 61.2. Is that what you said? 30.8, 61.2? Okay, 30.8, 69.2. See? And so for folks who, I'll go back to these. This one is 1988. I don't know when this one is. Oh, it says no way. Well, I don't know, maybe 1963, because that's pretty cool. It says Keokuk Junior High Science Department. So, my point is that those numbers are different than these numbers. And does it make sense that you could actually kind of update these as new information, new sampling techniques? People have too much time. So we're going to go with these percentages, and I'm going to show you how we can actually come up with how much does a copper atom weigh? 63.5496, AMUs. Okay, so just to kind of put things in perspective, don't let this throw you off. It says if you scale up from 100, if I scale up, not if I don't have 100 atoms, but if I have like 10,000 atoms, then I can move this decimal place over 2 places to know how many atoms of that type of isotope I have. So in 10,000 copper atoms, you see the 69.09% becomes 6,909. And if I have 10,000 copper atoms, then 3,091 of those would be the second isotope. All right, so switching gears from copper to something else, neon. Again, so I'm going to stop comparing my slides to those cards. But so neon has 3 isotopic forms. The first isotopic form of neon is the most abundant. So neon 20, what does that mean? 10 protons, 10 neutrons. Neon 21, what does that mean? 10 protons, 11 neutrons. Okay, less abundant, and the least, oh wait a minute, excuse me, I guess the second abundant would be this neon mass number 22. So it must have 10 protons because it's neon, and this one has 12 neutrons. Okay, so we have those three. It kind of says, then again, what if you scaled not 100 atoms, but if you had 10,000 atoms, this is how many of each one of these isotopes you'd have. Hydrogen actually has two naturally occurring isotopic forms. Regular hydrogen, and check this out, regular hydrogen is a mass number 1. It's like, wow, mass number is protons plus neutrons. So do you buy this, that regular hydrogen has no neutrons? Because hydrogen, it's got 1 proton. So with a mass number of 1, it has number of neutrons is 0. Okay, mass number of 2, 1 neutron. Mass number of 3, 2 neutrons. So if you hear people talk about deuterium, they're talking about hydrogen that's a little heavier than regular hydrogen. And tritium is unstable. But, all right, so here we have, and hydrogen's weird to have kind of cool names for the different isotopic forms. Usually not so much. We looked at boron a little bit ago, the 2 isotopic forms of boron. We looked at boron 10, boron 11. We have neon 20, 21, 22, and kind of the relative abundances over here. Magnesium 25, 24, 25, 26. Again, these are the mass numbers. So we could take the mass number, subtract the atomic number, or protons, to get the number of neutrons in each one of these cases. Now, sometimes in different classes, people have gotten into the habit of just using the atomic number. I know why we do it. The atomic number, okay, sorry, yeah, darn it, the mass number, which is number of protons plus neutrons, and we kind of use that as an approximate weight. And it makes sense because the protons and neutrons weigh about 1 AMU, but don't do it that way. If you have the real weight, use the real weight. So for example, see how copper forms 63, which has a total of 63 protons and neutrons. It weighs almost 63 AMUs. But what it really weighs, an atom of that isotope, is 62.930. Similarly, copper with a mass number of 65 doesn't mean it weighs 65 AMUs. Notice it's close to 65 AMUs. These are going to be integers because we're counting particles, and then this is actually going to be uncertainty associated with this weight, this mass. So 64.928 is close to 65, but not the same. Okay, so how do we come up with what's called a weighted average? And weighted averages aren't only just for weighing things, but a weighted average means that you weigh a factor relative to other factors differently. So this is the formula we use. Anytime you see in math, anytime you see this is the Greek letter sigma, and it means summation. Summation. It looks like an E. And what does the summate? What are we going to sum? Actually, for each isotope, we are going to multiply how much it weighs times its fractional abundance. And I have to kind of show you how we get to fractional abundance from percent abundance. And we're going to add them together. So it looks like this. Okay. If we're calculating the average atomic weight, we would take isotope 1. We would take how much it weighs times its fractional abundance. We would to that add another term associated with isotope 2, how much it weighs times its fractional abundance. Isotope 3, how much it weighs times its fractional abundance, etc. For however many isotopes we have. We end up having these kind of these products added together. So it's easier to show you than it is to kind of describe it. So in that formula, we need to get from percent abundance, which we're given, to fractional abundance, and here it is. All we got to do is take percent abundance, divide by 100. So with all that in mind, let's do an example. Let's pick on copper again. We'll use this data. One of the things I don't like about this example is, I don't know, I've got too many 60s. But that aside, we are going to go ahead and take how much they weigh times their fractional abundance, and we're going to add those two together. So here we go. So now you're up to something you can fill in. And I promise that there will be one of these on your next unit exam. It's not a threat, but it's a promise. So we need a first term to account for the first isotope. And we know that an isotope of that atom weighs 62.930 AMUs. Its percent abundance is 69.09. I need to get that to fractional abundance, and here's how I do that. 69.09 divided by 100. To that, I'm going to add now a similar term associated with the second isotope. So for the second isotope, we had a mass of 64.928 AMUs, and its percent abundance was 30.91, so its fractional abundance is 30.91 divided by 100. So do you see how I have weighted the contribution of these masses based upon the relative amount of how much they were present in Mother Nature? All right, and we get 63.55. So, see, periodic tables, they will update these. They'll update the isotopic information. As they update the isotopic information, then these all change. So, periodic tables can have subtle differences in it when it comes to the average atomic weight. That's one of those where I say, don't blame me. What was I going to say? Maybe that was it. But what we can't do, and I hesitate to even say it, but what we can't do is just take 62.930 plus 64.928, add them together and divide by 2. We cannot do that because we have more of this isotope, the first isotope, than the second isotope. We could do that if they were present in 50% each. Okay, so this is a kind of proof. You wouldn't have to do this all the time, but I'm just going to kind of walk you through how this works. If we recognize that one copper 63 atom weighs 62.930 AMUs, and then if we recognize that there are 69.09 atoms of this type of isotope in 100 copper atoms. Okay, and then we do a similar thing with the other isotope. Notice we end up with, the units cancel, we end up with, per copper atom, an weighted average atomic weight. Weighted average atomic weight? So this was what I was trying to explain. If we kind of round how much our isotopes weigh to using their mass number. If we round copper 63 to 63 AMUs, copper 65 to 65 AMUs, of course the number between them is 64. That would be what we call a simple average. But it's not a simple average. Since we had more of this first isotope, it's going to be skewed over here, and that's what our weighted average is. We could kind of look at an even more extreme case where we have most hydrogen is normal, like 99.95 or something is normal with no neutrons, one proton. Deuterium is present in a very slight amount in nature, and tritium not at all in nature. So if we do a simple average, we're going to come up with the average atomic weight of hydrogen should be 1.5. But if you look at the periodic table, and you'll probably be doing enough of these to memorize how much hydrogen weighs, you're going to see it weighs 1.008, and he was rounded to 3 decimals. So you're like, wow. 1.00. Wait, darn it. There we go. Okay. So, yeah. So this assignment's due to. Now I'm going to go ahead and do you guys have just a few more slides? Yeah. Okay, we'll take a look at these slides. But so this is also new. Okay. Now these are actually just kind of cleanup slides. We've talked about these concepts before, but we'll take a look at the slides. I could have kind of gone back and forth, but I didn't. As we've been talking about kind of how an atom is structured, we have the nucleus with the positively charged protons and the neutrally charged neutrons and electrons outside. This is trying to kind of show you that we said that the protons are kind of what helps the electrons stay associated with an atom. So we're showing you that the red is positive and the yellow is negative. And this is actually kind of showing you, perhaps we said that within the, I'll kind of draw our attention to the red here. Within the nucleus, we need those protons to kind of coexist. And so the neutrons kind of dilute this effect that we see, this repulsion between like-charged particles in the nucleus. This is kind of cool how the electrons kind of scoot away from each other. I can think of that as kind of the fluffiness of an atom in general. Remember, atoms are mostly empty space. It's this electron cloud. And this, I kind of think of, remember, well, if we pick on carbon, carbon 12 has 6 protons in its nucleus. And if it has 6 electrons outside its nucleus, we've kind of created what we call a neutral atom, and that's kind of what that's talking about. This says that this is talking about the attractive forces between the electrons and the negatively charged electrons and the positively charged protons in the nucleus. And forces like this actually get weaker as the distance increases, specifically as the square of the distance increases. So I've got a couple of examples here. We'll be talking more about ions. Here I have actually a lithium atom that has lost an electron and a fluorine atom that has gained an electron. And here I have an attraction between these ions. And this is trying to show you that as the, I'll do both of these. As the attraction is 2 units instead of 1 unit, notice the length of that yellow is showing you how strong that force is. So in the top one, where we have a +2 and a -2 being joined together, the charge is stronger, or the force is stronger than a +1 or -1. And this last one, actually, to me, if you compare the middle one with the bottom one, all that's showing you is that as the size of as the distance between the two particles with opposite charges decreases, the force increases, and that's kind of showing you the bottom one. All right, that's it. So we're out early. I think that's plenty because we're kind of switching gears. If you haven't got there, bring it Monday because we'll be working with molds and such. Have a good weekend.